as part of this exercise, and indeed as something that's going to be helpful for the coming assignment, or the assignment that's currently released, I asked you to implement Conway's Game of Life within Java. So this was, you'll recall, an implementation that originally had been in C, and the Java implementation is going to be somewhat different from the C implementation. I further have asked you to do some performance comparison between this implementation in Java and the implementations in C. Could you remind me, is that part of 9 or that's 10? Okay, thank you. So I won't be covering that then today, although I have my answers to it. So I split that up into 2 pieces. Okay. But I did ask you to implement Conways Game of Life in Java for today, and I'm going to be distributing my solution to it. And one of the things that I asked you to focus on for that implementation was to particularly consider how you implement rule-based abstraction, meaning we're abstracting over rules. In other words, we are trying to express this game of life in a way that will be amenable to providing several different rules to evolve cells. So one type of rule might say that a cell has to be surrounded by, between 2 and 4 live cells to survive. Another, by contrast, might allow it to survive even if the number of cells around it that are live goes up to 6 or something along those lines. So those are what I'm referring to as sort of cell evolution semantics, and we're abstracting over that to allow for expression of several of those rules. Several different liveness rules is, I guess, what I called them for the sake of the exercise. So how did you capture those liveness rules within your implementations? Yeah.
They all implemented an interface that defined a rule, and then you
Good.
3 rules that implemented the main interface.
Great. And I'll try to show that. So Warren hit on one very attractive way to do it, and it's a way that I used. It's not the only strict way, but basically the idea here is that compute liveness rules was declared as an interface, and it's an interface that's particularly simple. It is, in my implementation, one method, which is basically apply, and basically you give it a Boolean to indicate if the current cell is alive in the current space, and then the count of things around it that are alive, and it returns a Boolean which indicates whether that cell will be alive in the next time step, right? And then we have particular implementations of this, drawing an idea that we're going to be getting exposed to later today. So we're going to have a hash table which is going to map from a string, which requests which rule to apply, to a particular object which implements that interface. In other words, which provides a particular apply here. And I provided 3 such implementations, and each of them reflects sort of a static class where I basically say, okay, static meaning there's only one sort of instance of the class. That we don't need. We can have it within this class without being carried around by it, certainly. And this implements compute liveness rules. So compute liveness classic implements apply in this way. Compute liveness remain alive with 2 through 4 neighbors implements it this way, and the third one implements it a different way. And it looks like actually I have others as well. The point is, each of these classes implements this interface with a different particular implementation of this apply rule. Now, as it turns out, this is a little bit on the wordy side in terms of implementing these. What's an alternative to declaring a class here that implements them, saying, you know, this class implements this, and then in turn creating an instance of that class? And where is my hash table? There it is. Creating an instance of this class. What would be an alternative to that?
Anonymous implementation.
You have an anonymous implementation of the class. So rather than saying here new of this class, and that class is in turn defined per below, like one of these, in a way that implements that interface, we could instead have for example, a class which leaves apply abstract, and we could create an instance of that class where we fill in apply. Or we could actually do that with the interface as well, as I recall from the semantics of Java. So we could actually, instead of having here new this actual class, we could actually new a class that simply implements interface, but it's anonymous, and we only have to supply the apply method and we're fine. Right? That would obviate the need. It eliminates the need to define all these kind of classes which take up a lot of space visually but really don't add a lot. Instead, we could essentially provide these rules right here as part of creating this little hash table. So this classic would map to something that implements compute liveness rule, and we would specify right here in line the rule associated with that by filling in that apply method, right? So that would be more succinct. How many people took that option? It's going to bear on, okay, that's good. So some people are aware of it. I'll explain it a little bit more when we get to it later in the lecture, as part of a discussion of skeletal implementations. So here, we are implementing an instance of the class, and that instance of the class implements this interface. But we actually don't even need to do that in Java since I think Java 5 or something, we can actually just do a new anonymous class which directly inline provides the apply method. Okay? We'll see that a bit later in the lecture in more detail. But the basic idea here is we use, one way or the other, we use classes and interfaces, yes, to express rule-based abstraction. And so rather than passing around a closure, rather than passing around an anonymous function which remembers its state, what we're doing is we're really creating instances of objects. And those objects remember their state as needed, and they have certain methods that we'll then call that actually perform different things depending on the different objects. So the object created by newing this compute liveness classic, that will be an implementation of this compute liveness rule, and there apply will do one thing. It'll have one rule associated with it. This next one down, the second line, which handles this liveness 2 to 4, that will also be an object which implements the compute liveness rule, but its apply method will have a slightly different rule associated with it. It will allow for 2 to 4 sort of neighbors around it, inclusive, that are live for it to be live. Just to be clear here, we are using objects as our way of kind of expressing rules, and we do that because each of those objects has a method whose exact implementation differs from object to object that keeps track of its rule, right? If we did this in Scala, what would we use instead of objects here, naturally?
Case class.
Yeah, we could use we could use a case class. I mean, that would be an option. After all, in Scala, we have full access to Java interfaces and Java classes. But really, if you're seeing a situation where all you are dealing with is a single method here that differs from object to object, you might as well create a what? A closure. Yeah, a closure. You might as well just create a closure that applies the rule, and you pass that, you put that in the hash table, you put that in the dictionary, which basically maps from a command line argument to what to do when that mode is enabled. When the classic mode is enabled, we want to use this rule. It's easier to just specify it as a function, as a closure. And if needed, that closure can remember its state. It can remember some parameter associated with it and use that in performing the rule, just like an object could remember its state. So, ladies and gentlemen, in object-oriented programming, a lot of the ways that we achieve the flexibility that we like to use in functional style of writing programs is through objects. We create objects, and those objects have a state associated with them. They have some internal data, and they can apply rules in the form of methods. In the functional context, the way we do that is we create, very often we do it by creating a function or a closure that remembers some state associated with it. Remember, like, a closure that remembers I'm an increment by x function, and I remember my x. So every time someone passes me a number, I add x to it and return it. I'm remembering my state, just like an object remembers its state, and I know how to do my job when it calls the single rule that has to be applied. So here we're kind of using objects as if they are closures. And indeed, behind the scenes, that's what happens when you compile Scala code. And that's what happens when you use Java 8. They actually get turned into anonymous classes. And they remember their state, and they have a certain method. Okay? So, Conways game of life in Java. A few other things here. There's a little bit of difference in syntax, certainly. So we have different syntax for denoting, a 2D array here, for example, for denoting constants rather than pound defining them for the preprocessor. We say final int this to indicate it's a field, but it's a final field. It's a constant. It's an unchanging field. Normally in Java we use somewhat different case conventions, but I've sort of stuck to them from the situation with C. And we also have a little bit of awkwardness. My heart didn't leap up when I was writing this in Java. I didn't feel enthralled. And one of the reasons is Java as a language tends to be kind of wordy. It tends to be kind of longer in its expression. And there's a lot of things that I, as a developer, find really useful that you'd think they would have included in Java by now, but just never got around to it. An example is a pair. In Scala, pairs are just so sweet. The tuples, you just use these parentheses and you denote them. And here we have to say immutable pair, and you have to use it as a generic and say, okay, it's a capital I integer because there's this distinction between a lowercase int and an integer as an object. And it's just kind of wordy. You'll notice that in order to return a pair of things from this function, from this method, determine arguments, I need to sort of explicitly say, okay, it's a pair here, and I have to get it. And then having gotten that iteration count and rule pair, then what I do is I refer to its left and right items to extract the integer versus the rule from that pair. And it's just cruft. It's just cruft getting in the way of kind of nice expression. Once you've been developing in Python or Scala for a while, this starts to wear on you a little bit. It just seems so unnecessarily verbose, so unnecessarily sort of awkward. We have to create this whole thing to do a pair and refer explicitly to its left and right item. Why can't we just deconstruct it right here and essentially say, okay, the count iterations, comma, liveness rule equals determine arguments, and just be done with it. We were doing that back in the early 80s with languages, and somehow it's never penetrated to Java. Warren, yeah?
Yeah. I'm still kind of wondering what's the advantage of using that dispatch table over just having like in my implementation, I had an abstract interface called simrule.
Yeah.
And then I had a single variable that was the rule, and I just used its functions as necessary. So all I would need to do is declare my simrule at the very start of the program.
Yeah.
Then I just use its functions instead of passing it around using a hash table and all that.
Okay, the hash table was just used in one context. Thank you for asking. The hash table, so broadly what you're saying is exactly what's going on here. And you'll see it when I provide the implementation to you on Moodle. I mean, basically I'm providing a compute liveness rule that's being passed around. The hash table is used for one function alone. And that is to wit. That is used to map here from arguments on the command line to a rule in a count of iterations to perform. Basically, I use the hash table. So the idea here is that within this code, I am returning, I am looking up basically for the argument provided by the user. I'm looking up what rule to use as my liveness rule.
Oh, okay. So I could use an enum for that instead of that hash table.
Yeah, you can use enum or enum map is another possibility. That's not a bad one, I'll say. I used a hash table, but really the gist of it is you want to define at one place in the code, and I'm having trouble finding this place. Come on, classic. Where's my hash table? Come on. I told you Java was wordy. Hash table. There it is. So you want at one place kind of an enumeration of the different possibilities, and you'd like to be able to clearly indicate in this place in one, quite straightforward mapping for a given command line argument, what's the associated rule. You don't want that to be scattered around your program in different places, because that's inviting errors and kind of not really seeing the forest for the trees. And so I happen to put this in a hash table. It's an enum might do it more nicely, but the point is to consolidate it in one place in any case. And enum and enum maps are actually very flexible within Java. If I had another lecture or two in the class, I'd probably talk a little bit about some of the neat things you can do with enum maps. And one shortcoming of Scala, I don't know why they didn't do a better job with enums. But the hash table here is just used to provide one place where this mapping is stored so that you can look it up when translating from a command line argument to a particular rule. Okay? And that's easier than putting in the code explicitly when we do that mapping, because fundamentally the code that is doing that mapping, determine arguments, there's basically a whole set of cases which are basically the same, where we have some liveness rule and some iteration count given. So we have an iteration count, and then we have a rule specification. And rather than hard coding each of those in a scattered way within the code with a lot of duplication, I basically said, okay, let's just have a single mechanism that, given the command line argument, grabs the rule for that, and then we can get the count of iterations, and we're done with it. So rather than handling each case in an ad hoc way in the code, which is verbose and potentially error prone, and it's just unnecessarily sort of crafty. Yeah. Java, Java gets the job done. Try and catch blocks around things to handle errors. We have instead of pointers, we are passing around references, right? So there's not a risk of pointer arithmetic and all that sort of weird stuff that can come with pointers. You're not going to get aliases, two things pointing to the same underlying local variable, for example. So Scala or Java is more constrained there. What you do have again is this sort of awkwardness with pairs, returning pairs. But in my view, it's better than passing around two pointers where those two pointers are, like int double stars, and then those are assigned each within the method in int star, which is really what you get in C. If you want to return two things in C, you can return them in an array, you can return them in a struct, you could return them, struct like a pair, you could pass in two pointers and have them both be set. And that's what I did in the C implementation, and I really didn't like it that much. It was pretty unpleasant to me. But that's kind of living in the C world. So here I chose to return things in pairs. When you see this in Scala, that'll be much nicer. We don't have to go through this.
Are we doing it in Scala?
What's that?
Are we doing this in Scala?
You got it. 2 weeks that remain. You folks are going to be busy. We're gonna do this in Scala, and that in fact is okay. I had a lot of internal fighting about what goes in the assignment and what goes in the exercises last weekend. I was working on it all day and did them all in a bolus. And I can't actually remember if the Scala version of this is, I think it's in the assignment.
Yeah.
Yeah, it's in the assignment, the Scala version. But I will, after the assignment is due, I'll provide my implementation of it, so you can see it. It's sweeter, as you'd hope. Okay. After doing Scala for a while, also, or Python for that matter, just all these types that you have to put in also get kind of cluttered. Nicer than the C implementation, and next time you'll see the performance implications of this. Anyone want to hazard a guess?
I think the Java one is faster.
Anyone want to? I'm not disagreeing with Nobleman. Anyone want to hazard an opposite guess?
I would say probably not. C is generally faster. It doesn't have as much overhead.
Okay.
Java, because they're pretty similar implementations in terms of style.
Okay. Very similar in terms of style. You'll be relaxing that. You'll see a Scala implementation that's very different from this, where it's done in a functional style, where you're mapping basically each time the space is updated, essentially you're getting a new space back conceptually, rather than using these buffers, which are sort of traded off. This is still using buffers here. That's what's going on here with these int. At least in C you could say like int double star or something. This is like int bracket. This is 2D int arrays. You have buffer even and buffer odd. You're writing into buffer even while you're computing buffer odd and going back and forth. Whereas in one of the Scala implementations, you'll actually just have it operate on a space and produce a space and produce a space and produce a space. Conceptually, it's quite straightforward rather than having these buffer even, buffer odd. One of the Scala implementations will also do that. Okay, so do you think Scala? So you're going to hazard a guess that Java will be somewhat slower, a lot slower, or a little bit slower?
Depends on how good the Java compiler is. I haven't had a chance to test that.
Okay. So this is good discussion. There are cases where Java will actually be faster for some things, There are other cases where C will be somewhat faster. In general, this is a somewhat unfair well, I shouldn't say unfair. I mean, it's just one data point. You should recognize it as such. A lot of the places where higher level languages like Java can be faster are things which require, for example, some parallelism elicited. Because in C, it's really hard to tell if two things point to the same thing, so you end up making very conservative assumptions as a result. You assume they must be able to point to the same thing, so you can't parallelize two operations. Whereas if you have a higher level language where you don't have to worry about that a local variable is pointed to by 3 different pointers or something like that, you can end up making simpler assumptions. Also, often you're leaving more to the compiler to do, and so it can do it in a way that is more efficient, or it can use its choices. So in some contexts, C can be faster than Java. In some contexts, Java faster than C, and you'll see with this one, no pun intended. One thing to bear in mind, just pursuant to what was mentioned earlier by Andrew, is that Java runs on top of the what?
The virtual machine?
The virtual machine, the Java virtual machine. And so what that means is that, well, there's a big motivation for that, which is what? Why run on top of Java virtual machine? I mean, there's many reasons, but what was one of the earliest formative reasons, do you know?
You can compile for the same machine regardless of platform.
Yeah.
The secondary one is that it doesn't mess with the global system. Like you can have C
That's
messing
right.
around with like memory addresses that change.
And actually, both of those were foundational motivations for it. On the one hand, it's cross-platform. The same basic compiled Java code, and the vision back in 1993, it wasn't a vision shared by many of the people here at the time probably, but the vision was that you'd have Java code running in your browser, and that the Java compiled Java, the jar file, so this was before jars, believe it or not. It was back with .class files were the only thing around. Your browser would load them in, and then you could run them on any platform. So if you were running a Sun workstation, or you were running a IBM PC or a Mac, they could all run the same Java class files. So that was a big motivation. But like Warren notes, another big motivation is by running in your browser, or by running, it was called the language of the internet back then, sort of how it was presented. It was going to be the language of the web. By running there, it would be isolated from your main machine, and it wouldn't be able to transmit malware. It wouldn't be futzing with your underlying machine, writing things out, or overwriting files on your disk, spamming you with all sorts of adware, that sort of stuff. So in short, security was also part of that motivation. But what this does mean is it runs at a level of abstraction a little bit higher. And traditionally, there's a lot of work associated with that. Because in the first few versions of Java, how did it actually execute on the JVM? Well, what would happen is it would compile to bytecode in the .class files or .jar files. This is bytecode. Have any of you interacted with Java bytecode? Oh, I feel for you. Yeah, it's really interesting. In an earlier version of this class, we actually had code generation. Students did code generation into Java bytecode as part of an assignment. It was a lot of fun. So you generate code to specialize a method. And Java bytecode is basically a stack machine architecture. So it pushes things onto a stack, pops things up, performs operations. Did anyone in this class experience the language Forth?
I've heard of it.
It's in what class?
370.
In 370.
Sorry, 370, yeah.
370. Okay, Forth is a stack machine language. So you say push this on the stack, push that on stack. You can use dupe to like duplicate the top thing of the stack. You could swap them, and then you say like add, and it adds the two top things on the stack. Remember that? I don't know if it brings back good or bad memories, but
We learned what stack machines were in 215.
okay.
Used them.
Okay, you use stack machines at 215. So the Java virtual machine is one of those. And in the first few implementations of it, basically Java was running, interpreting each of those bytecodes. So it would say, oh, here's the dupe. I'm going to go duplicate the top thing on the stack. You know, it would look at it and push another one, push a copy of it down. Or it'd say, oh, this is a swap. So imagine a little loop where it's doing this, and every time it's rediscovering, oh, I have a swap. That's the first thing in the loop. So it goes and it does the next few things, and then it comes back to the top of the loop, and oh, I have a swap. And every time it's reinterpreting the bytecode. It's sort of saying, oh, first thing in the loop is a swap. And that's not a very efficient way to do things. It's called an interpreter. Anyone written an interpreter here?
We wrote a fourth interpreter in 370.
Okay, I'm not trying to rub things in. I thought there was some rumor of this. You can imagine having, while you're running Java, the overhead of that. It's actually trying to figure out what each thing is and do it, and then figure out what the next thing is and do it. And in a loop, it's figuring out what the first thing is in the loop maybe 10,000 times while it's doing this loop again and again and again. Swap, swap, swap. And it keeps on figuring out it's a swap again and again, 10,000 times in a row. And so around 95, 96, what happened is the team doing the Java compiler, I think this was 96-ish, they basically made a big investment in compiler technology, hired actually one of my buddies in grad school, and Mark Reinhold, and basically implemented a compiler that on the fly, when you're on a particular architecture and you get Java code, it will compile it to native code on the fly. It's called the hotspot compiler at the time. It would basically, instead of interpreting it every time you see an instruction saying, oh, this is this instruction, it would basically take the program. It knows what architecture it's on by that point. It knows it's on a Samsung smartphone with this certain processor. It knows it's on a Xeon processor, or it knows it's on an AMD or what have you. And it will compile to the bytecode to that, the Java bytecode, so it doesn't have to reinterpret it every time. So it actually is just running that bytecode, but it has to do that really quickly. So you'll see next time what this yields in terms of performance, and we'll see some of the trade-offs associated with that. Okay. So Conways Game of Life in Java, I'll be posting this to Moodle, and for those who want to do so, you can build off of this one in your performance comparisons, or you can do so with your own code. Okay, this will be useful for the assignment as well. In general, cleaner. Is this? I should ask. In general, Java versus C. If you went to hazard a guess, per 1,000 lines of code, which of them, how many defects would you see in each language per 1,000 lines of code?
Less in Java.
Yeah, certainly in Java, you're doing things at a higher level, and that includes most notably memory management. Now, in this code, it's a little bit of a red herring here, because in this code, we don't have a lot of dynamic allocation going on. It's not like we're allocating new buffers over time and so on. But in a lot of programs, you are. And memory allocation is one of those areas where working in C, you just have to be really, really careful. Because it's really easy to have memory leaks, to have dangling pointers that point off into La La Land, but they don't point to any allocated thing, and you can still write to them. Or pointers that point to things that used to be allocated but are now deallocated. Now you can continue to write to it. Maybe you have a reference to it as a double star. And now it's actually an array of hints. And you're writing to it as you're writing doubles to it, and you're overriding this array of hints with these double things. Really easy to do in C. Really easy to do in C. So in C, you can actually get a lot of lower level errors. You're also dealing in C with a lot lower level of abstraction and thinking about things. Like when you go to duplicate a string, you're thinking, okay, it's 0 terminated, and you're thinking about needing an extra byte for that end null to indicate its end, and so on, in a way that in Java you don't have to worry nearly as much about it. So C tends to be prone to a lot of lower level errors that Java is not prone to. On the flip side, what this means is the programs we build in Java tend to be more complex, tend to be at a higher level, and they exhibit other types of bugs. Maybe it's a deadlock, for example, in a way that we often wouldn't have to deal with lower level C programs. Anyway, we'll see this more next time, okay? See it more in exercise 10. Any questions about this? Java. Which do people like more, the Java or the C implementation?
Java.
I miss Java.
I also like Scala, but C is like, I have to go to Google, type and think, what does this do again?
Yeah.
What does it do again?
What is this
Why do I need to look at-
three-letter word that has no context because C needs to be short?
Yeah, it's like, why are you trying to do this text?
Yeah. So I share your aesthetics. I think the Java is nicer than C. It has a lot fewer distractions and kind of little crafty bits.
Like I was able to delete like 20% of your code when I translated this.
Yeah.
Okay, that's
Yeah, which is a matter of some delight, at least in my mind. I love it when I can delete code. It's refactoring to eliminate things is a great delight. And yeah, C has got a lot of unnecessary stuff, and in a larger C program it would be even more so, because you'd have lots of low-level things having to do with memory allocation, having to do with sort of data structure maintenance, potentially string-related things that are just really easy to deal with. So with Java, you're moving up a level of abstraction, and you actually have Booleans here, like built-ins of language. Can you imagine that? Oh man.
It is kind of annoying having to cast them around when you want them to still be integers.
Yeah, mumble.
Yeah.
Yeah, okay, we can do better with that. I agree with that. I agree that it could be improved for that.
It's okay going one way because you can just say if one,
Yeah.
then you're good. You just say assign it to thing equals one. But the other way, you have to have a double if statement.
Yeah.
Or in a triangle, terms of a triangle.
Agreed, although I think, in fairness, one of the reasons I originally had ints here, I just didn't have the heart to do it in the end. I didn't have the heart to ask you to do it. No, I was going to turn them into bit vectors. and that would further let you appreciate some of the differences between C and Java. Actually, you find bit vector operations in C a little bit prettier, but I just didn't have that heart to sort of ask you to do it at the last minute. But this is kind of a travesty. I mean, you're keeping an int around to indicate is it 0 or 1. This is kind of where you could really do it with bit vectors, and you would get a massive reduction in memory size, but the code would be complex. It wouldn't quite be as involved as writing a fourth interpreter, but it would get kind of gnarly at times, I think. So anyway, that was the class that could have been. That was the revolt that could have been. Okay. Any other comments? Yes.
So one of the problems porting this to Java was Java doesn't have any pointer, and there's a lot of
Yeah.
stuff done in C pointers.
Yeah.
Another peculiarity of Java is you can't pass value by reference. And
Yeah.
I mean,
Well-
it's done by default. I mean, you pass the value, but the value points to a certain
Correct.
section memory, but you can't mutate the integers. You have to create an object and
Yes.
assign the integer to. It's kind of complicated rather than to.
I agree. I mean, this, a case in point. So I want to sharpen one comment made. I welcome those comments, and while I quibble a little bit with the words used to describe something, you've hit on a number of important issues. And an example of that is actually not here, but it's further up where I have this immutable pair back of an integer. This is what we call a boxed integer, meaning it's a reference to an integer sitting in a box. This is kind of a weird thing about Java, right? We have kind of integers which are sitting in a memory location, A. But we also can have, an integer, A2. Okay.
It's just an object. Rather than
that's basically, and we can say 1 here, and the difference between these two is here, A1 is this is A1 here, and it actually holds a number. By contrast, A2 here holds a what?
Pointer.
A reference, or pointer to a number. It's not a pointer with all the implications of that in C. I mean, in C, if you have pointers, with the exception of void stars, you can do weird things like pointer arithmetic on them, which and I say weird because I use pointer arithmetic. I've written probably tens of thousands of cases of pointer arithmetic, but you can get in trouble with pointer arithmetic pretty easily. Why is that?
You can reference parts of memory that have nothing to do with it.
Yeah, you reference parts of memory that are totally unallocated. And
It's really fun when you start unaligning your bytes.
yes, no, exactly. And so you treat this thing as it's a whole bunch of doubles, or secretly it's a whole bunch of ints, and so you can index into it a certain number of times and point to things halfway through a byte, or halfway through an int, rather, halfway through a struct, etc. Oh man.
Reading floating points in the incorrect order or over 2 of them is real great. You can do fun stuff that way.
So, if we have time, let me tell you a story. So, ladies and gentlemen, this is a boxed int. Okay? And it's boxed because it's put in a box. It's put in a memory location, and we have a reference to it. And what's gone on here is an instance of boxing. Okay? This may change what your notion of Boxing Day. But this is, this is boxing of this integer. So it's taking an integer that's just a number and it's turning it into something that's at a certain memory location. And we need to do this sometimes. Why are we doing it here? Well, why can't this just be an int? Lowercase, yeah.
Because it accepts a class.
Yeah, so exactly. So generics. This is what we call the generic. It's type parameterization. We have an immutable pair of 2 types. And the things given to it need to be reference types. They can't be primitives like lowercase int. That's a primitive value type, and it can't take that. It can only take references to actual class instances. And so you have to tell it to take an integer, and when you pass back that integer, it may start as a lowercase int, but it gets boxed up into one of these guys. And so you're absolutely right, Fahim, that goes on quite a bit, where you'd like to pass sometimes a lowercase int, but you end up needing to deal with a capital I integer and go back and forth between it. And it's just not very, it's not very elegant. Again, just like so many things in C, it distracts you from the high level thinking about what you're trying to achieve into the minutiae of, oh, is this boxed or not, and this has to be boxed. It distracts from your overall thinking. But I do want to make a distinction, though, and this is an important thing which people in this class should really know about, a software engineering class. Because you used the term pass by value and by implication pass by reference. And I want to make a distinction between these things, because there's languages where you have the choice of pass by value and pass by references, pass by ref. And the terms are sometimes misused for Java and other languages. So in C, in C family languages, and Java is an example, the standard way of passing things is in fact passing things by what? By value. Okay? By value. So when let's distinguish between this. Suppose I have a method foo. Okay? And here I take in an int v, okay, and I am going to take in, okay, like this to be a better example. Okay, suppose you pass this in, and I say in my method v equals 2, and I call foo, and let's suppose I have here int a equals 1, and I call foo on a. Right? And if I here do a, depending on language, printf or whatever, here of a, what am I going to see? Yeah, I'm going to see 1. Why is that?
Because you're just passing the value.
I'm passing the value. So this A, the value of it gets pushed on the stack. It gets basically packed away to pass to foo. And this is going to get a value where v equals 1. And it's going to assign to this v, but this v only is local to foo. It's not changing the A pass to it, which is just, after all, a value. And so it's going to assign. And if we down here referred to v, it's going to be the value 2. But it hasn't modified this guy at all. Are we comfortable with that notion? Okay. So I'm going to expand this notion. Okay. And I'm going to have to expand it in 2 ways. One way. So this is called pass by value. Okay. Let me refine this a little bit more. Suppose now that A is not in fact a primitive value like 1. Suppose it is referring to a person. Okay? And it's referring to the person Joe. Okay? It's referring to some Joe. And now, foo, it's going to take in, I'm going to say informally, it takes in a person, and it's going to set, oh, let's be clear. Here, I'm going to say I set it to new person, and that person is going to be Jill. Okay? What's going on when this is no longer an int, this is I say it's a person. What is A really? I say A is a person. It's really a what? A reference to a person. So it's some reference off to an instance of the person class, right? Okay. So what happens when I pass it to foo? What gets put on the stack? What gets given to foo?
The reference.
The value of the reference. As normal, got it. It's the value of this reference that's given to foo. It's still passed by value, but it's giving it a reference to an object. So P here is referring to what?
Copy of the reference. Or
Okay, it's a
value
copy of the reference. Is it a copy of this person, or is it to the same
The same one.
instance? It's to the same object here,
It gets
right?
dereferenced automatically
Yeah.
in Java.
So here we're still at pass by value. It's just the value happens to be a reference.
So if you assign P, nothing happens, but if you do P dot something.
Correct.
we'll fix that.
Correct. So here, if I assign to P, basically within this code, it's just like assigning to V. It doesn't change the underlying thing. It's just now P points to a different reference. P is pointing to a different reference. And that's perfectly legit. Students sometimes get confused about this. In Scala, you could have something that's in reference to an immutable object, and that doesn't mean, you could have a var that's a reference to an immutable object and assign it a reference to a different immutable object, and that's perfectly reasonable. It doesn't mean the object itself is being mutated. It means which object is being mutated, which object is being referred to by this var is changing, and that's a different thing. So here, P is being set to point to a different person, to refer to a different person. However, if I said instead here, P dot, address equals would that change this underlying thing? Yeah, it would change this underlying representation. So what's being passed here is a reference to this thing, and if I mutated it, it would mutate this particular one in a way that this might see, right? This might subsequent see, that, it might affect the subsequent flow over here of the thing that called it. Are we clear about that? This is kind of foundational things, but I'm trying to draw a distinction on a very important point that I'm going to get to. I'm still leading up to the kicker, okay? Okay, now, there are some languages. I wish chalkboards had an undo button. They don't have that yet. Ladies and gentlemen, there are languages where, so this is all passed by value. We're passing, sometimes the values are references. Values are a reference, and that's fine. It's fine, it's still passed by value. There are languages, however, where we have passed by reference semantics. And languages within the C family where we can explicitly indicate, I want this thing to be passed by reference. How do you do that in, well, okay, we'll get to that. So I had a fellow grad student when I was at MIT who was really, really good teacher. He still is a good teacher. And every lecture he would use the board and only the board. He wouldn't use slides. And before PowerPoint. Can you imagine that? So he would plot out exactly which board he would write which thing on all through the lecture, and he'd reuse boards, So he might go 2 passes through the boards, and he'd know exactly where he's going to put each thing. I'm not nearly as sophisticated. Okay, so let's consider a language. So now, which has passed by reference semantics. Here we would have something. So remember before we had foo, and it took in an int v. Remember that? In one of these languages, we could say something like by ref. Generally, it's not the default, although for some languages it has been the default. Int v. Anyone know a language which has this? Some of you might have seen it in high school.
C# does, I think. And I'm guessing BASIC then if you're talking about it.
Yeah, Visual Basic has it. So VB, VBA. But yeah, we'll get to the C++ version of it. And does C# have byref?
Mm-hmm.
Oh.
I've never used it because why would you do it when you basically got Java?
Shiver me timbers. Okay, that's really I thought C# was a nice language. Now I'm
No. C# is like kind of spiky Java.
yeah. Okay, so ladies and gentlemen, here we could declare this being passed by ref. Okay, so over here we're going to have code. What was it called over there? A. Okay. Int a equals, what was it, 1? Over there, yeah? So this is going to say v equals 2. And then I'm going to call off to foo. And then I'm going to say printf. I'm just going to say print, because we're abstracting over languages here. Okay, so in this language where we're passing this by reference, what's actually being passed to foo?
A's location.
Yeah, it's kind of conceptually it's A's location. It's actually not passing the value in A, it's passing a reference to A. So when we assign v equals 2 and we return and print out A, what are we going to see? 2. Because we're passing this by reference. We're passing here not the value in A, but a reference to the L value, the location that holds that of A or whatever is being passed here. And that location is going to be updated when we say v equals 2. Okay. Now in C++, the way we denote this is what? Anyone remember?
Ampersand.
Yeah, we do it with ampersand. So, sorry, I never learned how to draw an ampersand.
You do it on call rather than on definition.
Something like that.
You draw a C, then you draw a D connected to it, basically.
Okay. I'm gonna a C and a.
And then from that, just keep drawing a D.
Okay. C. Okay. D. That's
Overlapped.
Okay. Somehow this is. That looks kind of like a kangaroo. Yeah. No. You get the point. Okay. Thanks. So, ladies and gentlemen, in C++, we can basically take in a reference to a certain location and do something very similar here. And this is really useful because, among other things, it allows us to do it without. How would you do this in C? This is C++. How would you do it in C? You'd pass a pointer to an int. And you would pass explicitly in C, you'd pass an ampersand. Not going to try it. You'd pass an ampersand A. But in C++, you can avoid doing that by passing a reference to this, and then syntax-wise, you just pass A, but it's really passing the reference to A. Which, I don't know about you, but it gives me the heebie-jeebies. Because you look at that and you can't actually tell it's a reference being passed. And so you legitimately would look at this and think, well, wait a minute, there's no way it could modify A in there. But in fact, you're passing a reference in a way that it could be modified. Okay. So Java is a pass by value language, which frankly I think simplifies our worries about it. But a lot of the values being passed Fahim is exactly right, are references. The references to boxed values and stuff like that. And some of those references might be mutable. References to things that are mutable. Passed by reference, passed by value. Okay. Any other points to talk about with this? So you're back to the high life again with Java. Soon you're going to be really enjoying Scala. Okay, I hope that's not an order. Okay, but let's stop that and let's get on to the main lecture. Sort of. Okay. So we will save this away.